Let us start lecture 3, and in lecture 1 and lecture 2 we have just introduced the importance of phase diagram, and at the end of lecture 2 we have started defining some of the important aspects of a system, and here system means thermodynamic systems. Now, we will continue our journey to understand or to define some of the important terms associated with systems. And at the same time, we will try to introduce one important concept which is called equilibrium. And this understanding of equilibrium is extremely important in order to understand the phase diagram, as well as the calculation of phase diagram. One needs to have basic fundamentals of equilibrium. Okay. So, we have defined phase, we have defined systems, and in the systems we have talked about three. One is closed system, one is open system, and one more system which we introduce, which is called isolated system. And if you see, closed system means it does not allow mass flow with the rest of the system. Okay. So, with the surroundings, what I mean that a system is basically surrounded by a boundary, and that boundary does not allow any sort of mass flow through that boundary between the exchange between surrounding and the system. But this boundary what we have in case of closed system, there could be two types of boundaries. One is diathermal boundary, one is adiabatic boundary. And when we talk about diathermal, means it allows heat exchange with the surroundings. The system can release it, system can accept it depending on the temperature of surrounding as well as system. For example, if the surrounding temperature is low, if that system has diathermal boundary, then heat will flow from system to surrounding, and vice versa. If the system temperature is low, surrounding temperature is more, then heat will flow from surrounding to the system. And that way we can get a lot of informations like whether the system will do work or system will receive work, okay, depending on the change in the system parameters as well as system properties. Like for example, if we consider isothermal system, and in case of isothermal system, if system needs to do work against an external pressure, then heat should flow in, and if the outside pressure does some work against the system pressure, then definitely heat has to go out, okay, considering it is an isothermal process. So, we will try to also learn this isothermal different processes. Isothermal means the temperature of the surrounding and temperature of the system both are same. So, that means they are in isotemperature condition. Iso means same. Now, once we learn these two boundaries, adiabatic boundaries and diathermal, we have talked about diathermal, which allows heat flow, but does not allow mass flow. But there is one more boundary which is called adiabatic. Adiabatic does not allow mass as well as heat flow. So, then the system will be isolated. Okay. So, isolated means it does not have any interaction with the surrounding. Okay. So, it acts like a kind of independent entity. Fine. So, this isothermal system can let us know one important aspects like there will be a term, we will be discussing that term called entropy. So, what happens to entropy in case of isolated system? Okay. But of course, open system means though we can visualize a boundary, okay, but that boundary can allow mass as well as heat flow. That means boundary you can think of a kind of imaginary boundary, or you can think of a kind of a porous boundary which allows both heat and mass flow. Fine. So, but you will see as we go ahead that the closed system will allow us to understand many of the thermodynamic concepts. Okay. So, let us talk about process. Since we have talked about systems, let us talk about process. The process could be, so we see lecture 3 topic definition of important terms. So, let us talk about process. So, we can say isothermal, we can say isobaric. Okay. So, isothermal means temperature does not change. Isobaric, pressure does not change. Fine. So, these two conditions we will be dealing with. Now, let us also talk about, since we have talked about temperature and pressure, let us talk about parameters, properties, characteristics of a system. So, let us talk about properties of a system or parameters or characteristics. So, for example, pressure and temperature both are properties of the system. Now, it is basically a kind of physical attributes or characteristics which can define the system. So, we will talk more about defining system. How do we define a system? Okay. And remember, whenever we talk about system, it is thermodynamic system, because we consider a kind of temperature, pressure, volume conditions. In case of multi-component system, we consider composition into system, into considerations. Those are the things. The physical attributes. So, now under physical attributes which can be measurable, fine. Some properties or parameters are easy to measure, but some properties are difficult to measure. For example, if we talk about pressure and temperature of a system, let us say I have a ball, okay, a football. So, I can decide how much pressure that ball has with the help of pressure gauge. I can also measure the temperature with the help of a thermometer, okay, fine. So, that gives you overall system temperature and pressure. Those two things are very easy to measure, but the equipment used for those measurement is easy. For example, I can also measure mass, okay. So, it is fairly easy to measure. Of course, depending on the mass amount, for example, let us say I want to measure a very small tiny mass and I do not have equipment, then it will be difficult. For example, let us say my weighing machine can measure up to the level of microgram, but if I have nanogram weight, so that machine cannot measure. Okay. Similar condition exists with the help of, in the case of pressure and temperature. If it is extremely low pressure and the equipment is not eligible to measure that low pressure or high pressure, of course, we cannot measure. But within our understandable systems, for example, when we talk about our phase diagrams, we will be talking about atmospheric pressure condition. And even if we talk about a different pressure, that pressure can go down little bit or go up little bit with respect to atmospheric pressure, which is considered to be 1 atmosphere considering a sea level condition. Okay. Now, temperature also, it can vary hugely. Okay. So, it can vary from 0 Kelvin to as high as possible, but our system, you will see that our system most likely will be considering, in case of single component, a little less than 0 and little more than 0, okay, little more than 100 degree. Why? In case of water system, 100 degree Celsius considering 1 atmosphere pressure is the boiling point. In case of ice formation, 0 degree Celsius at 1 atmosphere is the ice formation temperature. So, that means water to ice form, the liquid water to solid water forms. So, like that way we will be around that zone. In fact, while doing that, we will also consider some of the low temperature, low pressure regime also, fine. But in case of binary systems, more likely most of the cases, in fact, we will be only considering a room temperature to melting point of some of the metals, because we will be considering only the metallic phase diagrams and that to binary. Okay. So, we will cover only those in that temperature regime, okay, a little more than that, little more than melting point of metallic components, fine. So, that way our equipments will be what will be available with us will be enough, will be sufficient to measure those temperature pressure. But for example, let us say I want to measure entropy, okay. So, entropy measurement of a system is pretty difficult, okay. So, we have to use some experiments, some other means to calculate entropy. So, in fact, later on you will see that whatever idea we get to define a system in terms of entropy, that idea has been modified, and then instead of entropy we take pressure and temperature or volume of volume and temperature to be our independent parameters, which can be varied independently in order to define the system. Okay. So, we will leave aside entropy in our variable. So, that is smartly done. So, we will see how smartly it is done, but entropy definitely is very difficult to measure. Now, free energy, again we can measure free energy with the help of some equations. So, we will develop those equations. Even enthalpy, which is the heat content of a system, and that too has a pressure effect. So, the heat content we can also measure with the help of system parameters, which can be measured like pressure, temperature. Okay. For example, internal energy, we will see how to define internal energy. So, that can be measured with the help of volume as well as temperature. So, we see that most of the time we are moving away from, we are actually trying to smartly get away from entropy variable to pressure, temperature and volume variable. So, some parameters will be easy to measure, some parameter will be difficult to measure, but our smartness should be how to define system with the help of measurable quantities like pressure, temperature, volume, and in case of multi-component system we will take help of compositions, and their composition will also be converted into another thermodynamic parameter called internal energy, called chemical potential. Sorry, so it is not internal energy, it is a chemical potential, we will take care of it in order to define a system, fine. So, now, there are two types of properties, one is extensive, another one is intensive, fine. So, of course, there will be difficulties in order to measure those parameters, some of the parameters like entropy, but there could be another attribute to those parameters. What is that? Extensive means the properties should consider size of the system. For example, like mass. So, one system has a low mass, another system can have more mass. So, that means the mass is changed, the size of that particular system. Then we can also have, for example, when we talk about free energies like G, like H, like entropy, those parameters will be extensive quantity because those will be dependent on size of the system. Now, there are few parameters which are independent of size of the system. What are those? For example, density, a classic example. Density, what is the unit? We can say gram meter minus cube. That means gram per meter cube, okay? Or we can say kg per meter cube. That means whether I take 1 kg or 2 kg, if a homogeneous system we are considering, let us say a particular phase which is homogeneous system. So, that phase density would be nearly same all across. Of course, there could be bit of variations, those variations are because of the fluctuations within the system, but overall the density would be all places will be same. So, that means it does not matter what size we are considering and what size of the system we are considering, density one such. Then pressure. Pressure is also independent of size of the system. Temperature independent of the size of the system, considering a particular phase is in a kind of, when we talk about a particular phase, homogeneous and physically distinct region of a system, or itself can be a system. So, those. Then we will see chemical potential. Chemical potential is termed as mu, or there could be another term called G bar. Okay. So, instead those kind of information will come later. So, these are even surface tension. Those are intensive parameters. Okay. Now, we talked about physical attributes. Now, we have to define a system. We have understood system. Now, understood system means what is the definition of system, but now how to define it. Now, in order to defining, we need to have information of the system. So, one way to look at a system is, let us say a system has n number of particles. I can talk about atoms, I can talk about molecules. So, as well as, for example, our system contains a lot of sand particles, and those sand particles are moving, or the atoms are moving, molecules are moving. So, now our system, closed system, let us consider a closed system, and that system, every particle can have different properties. Okay. For example, mass of different particles, that can be different. Let us say velocity of different particles, it can be different. Okay. Like that way, their momentum could be different. Okay. So, like that way, I need to consider, in order to see, for example, if I know all those informations about those particles contained in a system, then I can definitely understand the system. But is it possible? For example, if we consider 1 mole system, there could be 1 mole of a metal. So, there could be n Avogadro number of atoms. So, is it easy to get information about 6.023 into 10 to the power 23 number of atoms informations? It is extremely difficult. Okay. So, now when we talk about those individual particles properties, we consider that a microscopic properties. Okay. So, if I know all those microscopic properties, of each particle, definitely we can define the system. Okay. So, what it exists, where it exists, how it exists. So, those existence can be understood, but it is difficult. So, again this is interesting, we always try to make smart move actually. So, that smart move, we actually moved away from microscopic property or microscopic nature of a system to macroscopic nature. Okay. So, that makes our life easy, and at the same time, in order to understand some process, those microscopic property, of course, it can give us much more information, but macroscopic property can actually explain some of the processes. Fine. So, we go from microscopic huge amount of information to macroscopic informations. Okay. So, one, that means when we talk about microscopic information of a system, we say that microscopic state. Okay. State means a kind of nature of the system, or thermodynamic state means, or we can say thermodynamic state of the system is the nature of that system, how it exists, but that is difficult. So, from micro, so that means when we talk about, so now we are talking about system understanding. So, or defining system. Okay. So, when we talk about defining systems, since we now after our discussions, we see that there could be a microscopic way to understand existence of a system, okay, which is extremely difficult. Okay. So, now in order to understand system, now how do I extend, how do I understand the existence of a system? Then, so this is coming in the pattern of microscopic state, or we call it microstate. Okay. So, for the time being we do not consider that. So, what will be my smart move? The smart move is, instead of understanding the velocity or the impact those particles are making on the wall, I will get a kind of average pressure, average load that is exerted on the wall. So, once I, and that to per unit area. So, once we know that what will be the average impact on the wall per unit area, we get a kind of information which is load divided by area, and that becomes a concept of pressure. Okay. So, pressure becomes in terms of Newton per meter square, so which is nothing but a Pascal. Okay. So, that you see, we do not consider how those individual particles are behaving. A system is there, a specific, let us say specific volume, and we are seeing what is the average load exerted per unit area, how many atoms hit the wall, and what is the way those atoms are actually hitting those walls, whether it is a tangential or normal, we do not consider that. We simply say that this is the load per unit area over the wall. Okay. That gives me the information of pressure. Okay. So, now we see pressure is basically a kind of average property. Similarly, temperature, each particle could have a different energy occurrence. Every particle can have a different energy level. So, those particles would have a different temperature existence, but overall that from outside, if I see the overall system, I will, if I measure what is the average temperature, I can also get to know the system temperature. Okay. So, it does not matter what those individual particles are behaving. So, again this is average property. Okay. So, now if I know pressure temperature, and then if I know the volume of the system, then definitely I see that what is the existence of the system, considering it is a mixture of ideal gases or a, let us say, single component solid or single component liquid. Okay. Or we can say it is a perfect mixture between different liquids or a perfect mixture between different solids. We will talk about those mixtures and how the solution forms. So, those kind of cases, if we know that what is the pressure and temperature, of course, single component system. So, for example, if we talk about single component system, we can definitely understand with the help of pressure, temperature and volume, we can define the particular existence of a system, and that particular existence of system, with the help of average property, we get to know the macroscopic state of the system. We get to know macroscopic state of the system. So, that means that is noted as macrostate. So, that means if it is a single component, let us say I consider single component, I know what is the pressure, temperature and volume of the system. Definitely I can see the existence of the system at a particular rest conditions. Okay. So, that is called macrostate, and the macrostate is actually a very important fundamental aspects of thermodynamics. We are moving away from a difficult situation to a kind of much simpler situation, and this simpler consideration can actually allow us to explain many of those physical processes. We will see that. Okay. So, this is macrostate, and in order to, for example, in order to define the macrostate of a system, we can, for example, if it is a single component, we know pressure, volume, temperature, but if it is a multi-component system, we know pressure, volume, temperature. At the same time, if we know the composition, definitely we know the very existence of the system. Okay. So, that means for example, if it is this is let us say I am talking about pressure, volume and temperature for single component system. So, I can understand its macro state existence. But if we consider binary component system, two component system, that time we have to introduce one more term because the composition is coming into picture. So, composition I can talk in terms of C. So, if we know all four, then definitely the system existence is defined. Okay. So, that way our entire phase diagram concept mostly will be talking about macroscopic parameters and the influence of those macroscopic parameter on the system to understand the phase evolution. Okay. So, let me stop here. So, we will continue our discussion on definition of different terms. Now, next class, that is the fourth lecture, we will begin to understand equilibrium, which is a very subtle and very interesting concept, and that if we understand, definitely we will be able to understand different other aspects of thermodynamics, and those aspects will define, will allow me to construct equations to draw phase diagrams. Thank you.